then there's this. And this is where you get to determine how you're going to lay out your components. The way this system was set up was that the gases leaving the furnace first encounter a superheater. The second thing they encounter is a reheater, and then we go on to the boiler. So that when we build our temperature duty diagram, we have something that looks like this, where the first thing is, of course, the superheater, the reheater, and the boiler, and so on. So it depends on how you set up the components. So for example, you could have it where the first thing you encounter is the reheater. But you would have to set up your temperature duty diagram accordingly and account for all of the energy transfers that you need. In this case, when I did the calculation, it starts out at a little less than about 971 degrees C, and as we march through the plant, or through the cycle, or through the components, we first hit the superheater, onto the reheater, and the boiler, and each time we lose energy in the flue gas. So how you arrange those components is up to you. You just have to be able to account for them in your sizing calculation. And again, like I said, this is based on having a configuration that looks like this.
Is there a specific geometry the reheater has? Is it it's a single tube that goes through? I mean,
yeah, typically they are, and I'll draw it on the profile, but it is essentially a tube that kind of folds over itself like this, and then it's connected to a header. And then there will be a multiple series of tubes, so that if I'm looking at it from the front, what I'll see is a bunch of tubes.
so it's similar to the superheater.
Yeah. So what happens is food will come in, like steam will come in here, and it'll move through, and then it'll come out the other end. And it'll be connected, like I said, in some of the header.
That wiring might be in the boiler, right? Reheat.
I'm sorry, what?
This is reheat, yes?
This is for a reheater. Single phase heat transfer.
Going back to the condenser, so if we decide to add another condenser, you're basically taking, say in our case, we have 3 power generation sets.
You have what?
3 power generation sets. So we would have 2 on each.
Is that how you're setting it up?
Is that not?
You're the designer.
Okay.
So if you have a power generation set that's the mass flow rate and all the states and temperatures and everything, you're meeting the power output requirements. Your problem now is, okay, I now need to condense that steam. And the problem you're finding is if I have one condenser, the heat transfer required is excessive, and I'm not able to design a reasonable condenser, in which case, okay, you're saying, I'm giving you the option of splitting that steam into, say, 2 condensers. And if you're having 3 identical sets, then you're essentially running 6 condensers.
Another question. When we're taking the thermal properties of steam going into the condenser, do we take just the thermal properties of the steam itself, since you have saturated steam, technically you have water vapor in there too, which would have its own thermal properties?
You're dealing with steam in the 2-phase region, right?
Yeah, saturated steam.
Oh yeah, but it's coming in at it's coming in. So you'd have a table of values. Remember, you have, when you're looking at your thermodynamic properties, you have properties of steam at elevated temperatures and different pressures, And then when you're dealing with saturation values, you're inside the vapor dome, and you're going to have for a given pressure, you're going to have a given temperature, a given saturation temperature. They're not independent. So you go to a table of saturation values. For thermodynamic properties, you have your thermodynamics tables that give you enthalpies and internal energies and things like that. In your heat transfer book, you have a table of saturated values that give you things like viscosity, Reynolds number, Prandtl numbers, and thermal conductivities and that.
In what book did you say that?
That would be in your heat transfer book.
Okay.
Yeah, Incorporate. And the other textbook that I use is the Moran and Shapiro for thermodynamics. And that's where I get the thermal properties. Now, I believe I also gave you a series of tables in the text for the heat transfer properties of steam at different pressures and temperatures for superheated steam.
That one's on Blackboard.
That's on Blackboard, and that's what you would use when you're dealing with superheaters and reheaters, because now you're dealing with elevated temperatures and pressures. But if you're dealing with the in the saturated values, you'd have the tables in the heat transfer book. Yeah. And I don't know if I posted those tables because they're in your heat transfer text. Unless you all hopped it, you should hopefully still have that. Yes, sir.
Well, after next year, how we can handle the pressure flow across the system component, or just the pipe
I'm sorry, what? For the pump?
Yeah. How we can handle the pressure flow across the system component?
What is your question? How do you handle the pressure drops?
No, wait, once we calculate the pressure flow, how we can apply this number into the sizing for the pump?
For the what for the pump?
For the size, I mean sizing
For the sizing for the pump?
Yeah, selecting the pump.
What's the question?
So how we gonna apply the number we get from pressure flow? Let's say for the condenser, superheater.
In other words, I have okay, this is my system. And what's your question?
So let's say the pressure drop across the superheater, it's 100 kPa.
Pressure drop across the superheater is 100 kPa.
So how we can use this number for pump selection?
Oh. And your pumping power requirement is going to be whatever your target is plus whatever pressure drops you're losing, because if you're, for example, if your goal is to operate at a certain pressure and have a certain work output, let's suppose that you're starting at, what is it, 8 kPa down here at the condenser, and your goal is to pump it up to, let's say, 10 megapascals. That's the system requirement, right? That's what you need to be able to pump. But the other problem that you have is you have pressure drops across the condenser and across the boiler and across the superheater, say.
Which also do over generic piping.
Yeah, and if you have frictional losses in your piping, so let's call that piping losses. So these would then be your delta P, what we'll call a loss. And now you actually have to pump this plus to account for that. So your pump actually has to account for those friction losses because they're essentially eating up some of that pumping power. So you would essentially add that to it, just like we would do for the when we were doing the pump characteristic curve for when we were looking at a pump, when we were doing like through a condenser. You're looking at what is the pumping power requirement that you need to maintain a certain head, plus all the major and minor losses. Because that has to overcome all that. Otherwise, what's happening is your system is going to get degraded by that amount, and you're not going to get the power output that you wanted. So, for example, when you weren't counting on pressure drops and everything like that, you got 70 megawatts. But then when you start calculating all the pressure drops, what happens is that, especially like outside of the superheater and everything, your pressure dropped a little bit, so now your enthalpy isn't what you thought it was. Because when you calculated it without enthalpy, you got an H1 is equal to some number. But then when you calculate it with the pressure loss, you're now getting an H1 that's something different. And that goes into your work calculations, correct? So you're not getting the work out that you thought you were. So if you wanted to account for that, you'd have to then put that in there. So that you'd actually have to operate a little bit higher or accept the losses. In which case you'd have to then design your system so that even after you take into account all those losses, you're still delivering a minimum of 70 megawatts. And this is why I cautioned you early on not to just settle for getting to 70 megawatts and calling it a day, but rather trying to put in some buffer because you're going to see losses in the system due to pressure drops. Yeah.
Is that, we have to do the same thing for heat loss or no?
No. We're gonna consider certain things to be adiabatic, so we're gonna consider things like pumps and turbines to be adiabatic in the sense that they're not, any heat transfer that they lose or heat loss that they lose is negligible in comparison to the work output. And we're also going to consider things like that condensers and feed water heaters and the like are insulated to the environment, so all of the heat transfer is taking place where you want it.
As well as the generic piping?
Yeah, for the generic piping, we'll assume that we're not going to be any negligible, any appreciable heat loss, just for the purposes of this project. Yeah.
When you calculate the pipe losses, it's given that from the boiler to the branch of your 4 turbine sets that it's 155 feet. What about the distance from that branch to the actual turbines? Is that
Negligible.
we have to include that?
Because then like you were asking, how detailed do I want the schematic?
So we don't have to include the
No, I'm not asking
290-degree
you to,
turns?
to come up and calculate the piping to each individual turbine and the piping from the turbines to the condensers and the piping from the condensers back.
So the pressure entering the turbines is equal to the pressure out of the boiler minus the pressure loss over that
Yeah,
155 feet?
Do it like that.
Okay.
Any other questions? Yes?
So in regard to the, estimating the length of the pipes, you just want us to go off the schematic you gave us?
Yeah.
Okay.
I'm not giving you any requirements on how you route it. That's up to you. So, you can do it with 80, you can do it, like I said, you can go out from here straight down and do a 90-degree elbow. You can do 245s. You can do something like this. However you work it out, and you can, do little trade studies to see which one is the most beneficial. But all I'm giving you is the overall location, and how you get from the superheater back to the turbine is up to you. Other questions? Yes?
For the handheld for the combustion, is it okay if we just show you how we got our numbers and put in Excel without having to write out the whole 6 pages that we're copying exactly anyway?
For the combustion calcs, because they are lengthy and tedious, you can go ahead and do abbreviate it somewhat. Okay? You could skip some of this, a lot of those intermediate steps and just go to the meat of it. But I do want to, because what I do when I'm looking at your reports is I do sit down and I will go through your calculations. So I will want it written out, like your sizing and all those things. I follow it. And if it's hard for me to follow an Excel sheet. But I can do this, and I will hope that you will have one of your teammates perform a check, because I sometimes find